Now let's consider liquid-based ion selective electrodes. Liquid-based means that the liquid ionophore is incorporated into uh, the matrix. Okay, so hydrophobic membrane is impregnated with hydrophobic ion exchange called an ionophore. Okay, let's look at this electrode. Here you take this glass tube, and then at the end of here there is a hole, and you put a hydrophobic polymer membrane here. Okay, this polymer membrane is simply a support. Okay, and you inside this polymer membrane you impregnate the hydrophobic ion exchanger, mm, and ion selective ionophore. It's ionophore here. So actually, you need several other species. For example, in this case, uh, the hydrophobic is a membrane, right? For example, you use this polyvinyl alcohol, okay, and then you need ionophore. So which one is ionophore? Here, let me see. This one, hydrophobic calcium ion binding ligand. This one, this is quite long and complicated molecules. Yeah? So NN dicyclohexyl N prime N prime dioctadecyl 3 oxapentadiene. Okay, this one is calcium ion selective ion 4. Okay, not only this, you need uh, others, the components like hydrophobic anion here and hydrophobic liquid solvent. Yeah? Or sometimes you need plasticizer, okay, to make this membrane soft. Okay, but the core is this one, hydrophobic membrane and ionophore. Okay, and yeah, that's it. And inside the liquid should contain the calcium ion in this case, because you want to measure the calcium ion concentration, and also you put here internal reference, usually silver chloride electrode. Okay, yeah, it's very simple, quite simple. And the the IAC equation is the same. A equals constant plus beta. Beta is always there. Beta is usually less than 1, and 0.05916 divided by 2. Why 2? Because calcium ion, it has divalent plus charge. Okay, and multiplied by log calcium ion activity. All other things are constant. Okay? So this is called liquid-based ion selective electrode. Okay, and you see, usually the ion selective electrode dynamic range is not very wide, which means that look at this one, this figure. This is the lead ion selective electrode. Okay, lead liquid-based ion selective electrode here. When lead ion concentration is high, like a log lead ion concentration is -2, which means the 0.01 molar, and down to here maybe a 0.1, this one -6, yeah, log concentration -6, which means that the lead ion concentration is 1 micromolar, yeah, up to this point. You see, potential is linearly changes with the log concentration of lead ion, but sometimes you need to measure the lead ion concentration much, way down to sometimes to 10 to minus 12 molar, right? But conventional, uh, the ion selective electrode only shows this linear. This is the dynamic range here, down to 10 to minus 6 molar, right? But how do we extend this dynamic range down to maybe a minus 12. Okay, do we need to develop a completely new ion selective electrode, or maybe, but maybe not. Okay, maybe not. How can we achieve this this linear range extension down to here, right? 10 to minus 12 molar, right? This is extremely low concentration, but it's possible even with conventional filling solution. Okay, yeah, I will show you here. Yeah, that's possible through the metal ion buffers. Metal ion buffers like acid-base buffer. Yeah, we you already learned acid-base buffer. Yeah, to make a buffer, you need weak acid and its conjugate base, or weak base and its conjugate acid. Okay, and the theory behind the acid-base buffer is rather complicated. Yeah, but metal ion buffer is really simple to make, right? It is based on the complexation, yeah, with a complexing agent. For example, let's consider calcium ion here. Calcium ion makes complex with what is the Y? EDTA, okay, the fully deprotonated EDTA, and it makes calcium EDTA complex, okay. And usually this formation constant is very high. Kf is 10 to 10.65, okay, and it can be written in this way. Yeah, if you are not familiar with this equation, you go back to uh, chapter 12. Yeah, EDTA titration. All right, and here calcium ion concentration can be written by this equation. You see, Kf is constant and alpha y4 minus value, this fraction is constant at a given pH. And what is important is that you can control this calcium EDTA complex concentration and free EDTA, total free EDTA um, concentrations. Okay, so by changing the ratio of these two concentrations, you can maintain the calcium ion concentration at constant. You understand? Yeah, by changing the ratio, this one, the metal EDTA complex concentration and EDTA. This EDTA means the sum of the free EDTA concentrations, and so this metal ion concentration can be determined. Okay, and then it can be constant as long as you maintain this ratio constant. So the metal ion concentration is maintained constant. Okay, that's the metal ion buffer. That's the principle. Yeah, very easy. Okay, very easy. How do we maintain this such a low concentration of metal ions? Because Kf is very high. Okay, so metal ion concentration can be maintained at a very low concentration. All right, that's it. So let's assume instantaneously this calcium ion is removed, for example, by the adsorption on the cell wall. Yeah, yeah. So on solution, calcium ion concentration may be it's lowered, yeah, because of the adsorption on the wall. Yeah, the beaker on the wall of beaker, for example. And then what? Since this one is already made constant, and then immediately the calcium ion here, yeah, from here is some calcium ion now is dissolved, yeah, from this calcium EDTA complex, okay, to make the concentration constant. Okay, so even though the very small amount of calcium ion is removed from this the calcium EDTA complex, the total this value is almost constant, yeah, not changing much. Okay, that's how this metal ion buffers work. Okay, very easy, and the theory is easy, and that's how So as long as you in this case, to maintain the lead ion concentration down to maybe a 10 to minus 8, 10 to minus 10, 10 to minus 12, yeah, you simply adjust, you look up the Kf for the lead and EDTA complex, and alpha y minus y 4 minus value at a given condition, yeah, and then you calculate the ratio, yeah, depending on your lead ion concentration here. Okay, yeah, that's the principle. Very simple. So here is this table tells the detection limits and the selectivity coefficient for liquid-based ion selective electrodes operating without leakage of primary ion. All right, and yeah, there are, you know, they have been developed the many ion selective electrodes based on liquid-based, liquid-based ion selective electrode. Yeah? And not only these ions, but also other ions. Yeah, many of them are commercially available. For the sodium ion, detecting the sodium ion concentration is very important, and the detection limit is 30 nanomolar. Okay, for potassium ion, 5 nanomolar. And here is it. This is the interfering, main interfering ions. Okay, and ammonia and cesium ion, calcium ion, and you see silver ion like that. Yeah? So for these ions, there are ion selective electrodes available. All right. Then next one is compound electrode. Okay, compound. Yeah, in Korean 복합 전극. Okay, 복합 compound electrode. Yeah, you take the ordinary, for example, glass electrode here. Yeah, this is glass electrode. Yeah, and glass electrode, you can sense the proton concentration over the wide range. And this one is divided for measuring CO2 concentration. Okay, CO2 gas sensing electrode. How do you measure CO2 concentration with this glass electrode? Yeah, principle is actually very simple. You see, around this glass membrane, you wrap with this membrane. Yeah, this blue one. This is the membrane, but this membrane is only permeable to CO2, not other gases. Okay, when the atmosphere, the carbon dioxide in atmosphere dissolves in water, and they make equilibrium, and then here in the that means that in water there is a CO2 dissolved. Yeah? And here, if we wrap this one, this CO2 permeable membrane, around this glass bulb here, and then only CO2 enters in this one, the membrane, and when CO2 enters this inside this membrane, and then this inside this liquid pH lowers. Okay, why? When CO2 dissolves in water, water pH is lowered. Okay, and then that lowered pH is measured with the ordinary this glass electrode. Okay, and then this pH change can be related to the CO2 concentration uh, in 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 liquid. Okay, yeah. And also that the CO2 in liquid in water is equilibrated with the CO2 in atmosphere. Okay, so eventually you can calculate the CO2 concentration in air. Yeah, that is compound electrode. So if you use different membranes for different gas, and then you can measure the different gas concentration. Okay, so you know the principle. Okay, very good. All right, let's apply standard addition technique with ISE. Okay, with ISE, and then you can apply a standard addition technique to know the concentration. You see, this is this equation is for the ion selective electrode. Yeah? E equal potential equals constant plus beta. Beta is also constant, and this part, okay, this is a proportional constant, and then logarithm of concentration x. Okay, and then when after you arrange this equation, all right, taking the 10th power, okay, and then you reach this equation. Yeah, this one looks quite complicated, okay, but let's look at in detail. This left hand side, it is it's y, yeah, it is v0 plus vs multiplied by 10 to e over s. S here is this one, beta rt over nf, okay, beta rt over nf. This log 10 is a 2.303. Yeah, this is also constant, right? And the right hand side, you see this one, 10 to k over s multiplied by v0 cx. V0 is initial volume plus this part, okay, and here you see vs, all right. Vs is what, added the volume, okay, and then this take as x vs, and this whole part on the left hand side takes, we call it we assign that is y, and this is constant, and this is p, y intercept, okay. This is the slope. So what we do is that to measure to you measure the electrode potential here, and then you apply this one. Yeah? V0 is known, and Vs is, that's the added volume, is known, and then you calculate and take this one as y, and this one is s, and then you get this type of data, and then you apply the linear least square method, yeah, to get this not this y-intercept but this x-intercept. You extend this line until it meets x-axis, okay, and then this x-axis is it meets at the negative value of x-axis, okay. Yeah, x-intercept here is that minus p over m, yeah, and then it is minus v0 cx divided by cs, okay, and this one. And then of course you simply remove this negative sign, okay. That's how you measure the concentration, okay, cx unknown concentration, okay. So standard addition method is a general method for obtaining unknown concentration, yeah. Usually three techniques are used, yeah, to determine unknown concentration. First one is you set up the calibration curve, and then second one is to use internal standard, and third one is the doing the standard addition. Yeah, this technique can be used with ISE. Yeah, all right. Okay, now our last topic is the solid state. Okay, solid state chemical sensors. Okay, uh, using for transistor. Yeah, yeah, so this topic is very uh, unfamiliar with you, but it is also very important. Okay, um, you see, applying the semiconductor technology, it can be used to make the solid state sensors. Actually, transistor sensor. Okay, the transistor is everywhere. Yeah, transistor made a revolution in electronics and in our the society. Okay, and it can be made very small. Yeah, this is pH sensitive FET. FET is field effect transistor. There are several types of transistors. The original transistor is what bipolar transistor, right? The inventor, three inventors were awarded the Nobel Physics Prize, okay? And then this electronics has been what mm, the progressed a lot, yeah. And then now most transistors are field effect transistor, okay. I'll show you the principle briefly how that field effect transistor is working, yeah? Anyway, the important is that pH electrode can be made very very small, yeah. You see, yeah, this is your finger and very small, and since it's made of what silicon, yeah. The silicon is a very stable material, so you can insert this very small pH sensor into a very small area uh, under the very harsh condition, okay? That's the beauty of this FET based chemical sensors, okay. Here this is another view. Here is the pH FET pH sensor here, and here is the thermistor. That means what? Thermistor is to measure the temperature, and also you need a reference electrode, yeah, to take the potential difference. Anyway, uh, since this is made out of a semiconductor, intrinsic semiconductors are silicon, germanium, and gallium arsenide. This is the compound semiconductor. Okay, silicon and gallium, germanium is a very well known semiconductors. Yeah, they belong to group 4, yeah, group 4 element, okay. The gallium arsenide is also a very promising semiconductor. Gallium belongs to the group 3 elements, and arsenic is group 5, so average is group 4. Okay, let's consider silicon only. And silicon has 4 arms, okay, 4 pairs of valence electrons. But when you dope with, for example, this uh, group 5 element like phosphorus, okay. So I'm sorry, yeah, this is I'm sorry. Oh yeah, this is group 5, and then it has 5 arms, okay. So the outermost the shell, it has 5 electrons, okay. And then 4 electrons are used uh, to make a bond with silicons, and one this electron is left, okay. And this electron is moving rather freely in the silicon, okay. This is called n-type silicon, yeah. And in n-type silicon, this electron is the major carrier. But in the meantime, if you add group 3 element like aluminum aluminum has 3 arms, so this one arm is missing. In that case, the whole is this is there is electron vacancy is the main carrier, okay. This is called p-type silicon, okay. And then how do we apply n-type and the p-type semiconductors? Usually we made a contact like this one, okay. So p-type and n-type semiconductors are made contact. This is a physical contact, and if you apply plus voltage to the p-type silicon and negative voltage negative terminal to the n-type silicon, and then current flows, yeah. This is called forward bias. But in the meantime, you reverse the potential biasing, and then here in p-type silicon, yeah, this one, holes are attracted to the negative pole, and the electrons are attracted to the positive pole. So the current, the very very negligible current flows, virtually no current flows here in this case. But in the forward bias, current flows. Yeah? This is a reverse bias. An important thing is that in the in the this contact, this is contact area, right? In the here there develops a depletion region. Yeah? This thickness is about 1 micrometer, yeah, very the thin layer is formed. Okay. Anyway, yeah, these two the phenomena can be usefully used to make a transistor. For example, this is field effect transistor. All right. Okay, let me explain in detail. Here, in a silicon base, okay, the silicon base, and this is silicon base is p-type silicon, okay, and then on the top, and here you make n-type silicon, okay, and this one is also n-type silicon, okay. This is separated, yeah? And then in the middle you put the silicon oxide insulator. Silicon oxide. This is very. This is insulator. Yeah? Resistance is very high, and then on top of the silicon dioxide, you uh, you put the metal layer. Okay, metal is conductor. Okay, and then now you measure current between this n-type silicon and this n-type silicon, and this n-type silicon is called the source, and this one is called the drain, and this one, yeah, this p-type silicon is called the base, and this one, the this metal contact silicon dioxide, this is called gate. Okay, and how do we operate this semiconductor? So the current between this one, source and gate, okay, so source and this drain can be controlled by this gate potential. Yeah, do you follow me? Yeah, although yeah you don't follow me, yeah, that's okay, but try to understand. Yeah, and your textbook explains well. Okay, let's think about that. Yeah, when you apply a potential positive potential to the metal contact, right, at this gate. Okay, since the metal is a conductor, but silicon dioxide is insulator. So when you apply positive potential here, yeah, it creates, yeah, this positive potential creates here the kind of channel, okay, create electric field here. Okay, yeah, this is the case. Okay, electric field. Okay, so electrons can they be transported between the source and drain, right, because through this channel. Okay, you understand? But when this is negatively charged here, and then this the channel is not formed, so no current flows. Okay, but now here is the point. Now electronically, by changing this um, potential to the gate, yeah, you can create or not creating this channel, but that can be done. Yeah, this electric field can be done by the ion adsorption here. Hmm? You understand ion adsorption? Okay, let's look at this one. This is the same transistor, and here instead of using metal contact here, you put chemically sensitive layer here, yeah, and then here is your ornate solution. Okay, so let's assume this chemically sensitive layer is very sensitive. Yeah, this is the ion selective layer, and then it is sensitive to, for example, calcium ion. Okay, and calcium, in the ions in ornate solution, many of them are what bind to this layer. Okay, positive ion adsorption here that creates positive electric field, so you can make this kind of a channel, right, and then current flows. You understand? And what? So current flows, and in the externally, you develop this kind of circuit, and then you change here the let me see. Uh, yeah, right here, although you don't need to understand this circuit, but the idea is that you change this this variable voltage, yeah, voltage source, and then you can make this current 0, okay, and then you read this voltage that follows, yeah, this voltage follows the ion selective electrode equation. All right, yeah, that's the answer. That's the how it works. Okay, this is very complicated, and I think I don't think this is easy to make. But anyway, the principle is like that. So transistor, field effect transistor, can be used as a chemical sensor. Okay, why this type of electrode is needed? As I said, this one is all made of solid state, and this is very stable, and then can be made very small. All right, and then you can use in a harsh condition, and also you can monitor the ions in a very confined area. All right. Okay, and for the anion, sensitive electrode, yeah, the same principle can be applied. You use here the anion selectable, anion 4 is here, and then you can uh, generate negative, the electric field here. Okay, so this one, this electrode, the field effect transistor, chemically sensitive field effect transistor has been developed to measure ammonium ion, calcium ion, nitrate ion, and CO2. Okay, yeah, and so this figure tells that. So usually for the anion, we take the positive potential, positive slope, and for the anion, we usually plot, to make the slope negative. Okay, yeah. So voltage must be applied by external circuit here to bring the current back to initial value, represent the response of the device to silver, in this case the silver ion. Okay, yeah. Okay, this is the end of chapter 14. Okay, I selected several problem sets. Yeah, actually, all the problems are very very precious and very very important. Okay, and then I strongly encourage you to try to solve everything. Yeah, and then you find the solutions from the internet, right? In Google, you type solutions manual of quantitative chemical analysis, 8th edition, and then you can immediately find the solution. Okay, I cannot upload the solution in eCampus, right, which is against the law. Okay, let's stop here.